This video is for all the scientists around the world. I want to gain your guys' respect. I want to win the Nobel Peace Prize on standardizing physics with my equations, which will also combine the use of chemistry. I will show you guys that on different videos. But to get started, we have to have a standard length, time, and mass. We're going to keep the time, which is based on a cesium atom. But our mass, we're going to standardize mass and our length, which is based on the speed of light. Because right here it talks about it wants to have mass, but we don't have a scale that's precise enough to really give a standard mass. So instead, I'm going to come up with my own. And then what we're going to do is base it off of chemistry. We're going to estimate the number of atoms to get our weight. And then we're also going to be using the size of an atom, the length, to determine our standard length that we're going to use for my physics. So I don't have that much memory on my phone to record. It's only an 8-minute video. But I wrote everything out already. I was going to show you guys step by step, but I might as well just walk you through it because I don't have enough time. So here's the hydrogen atom. Here's with the radius of just one atom of hydrogen. When it's bonded, it's at 0.74 angstroms. So what I did is I took 1 centimeter because I want to combine this with the SI unit. So I took 1 centimeter. 1 centimeter contains 10 to the minus 2 meters. 10 to the minus 2 meters is equal to 1 angstrom. 0.4 angstroms from the hydrogen length is equal to 1 hydrogen bond. And in total, it gives you 135 million hydrogen bonds. So you get the 1.35 times 10 to the 8 H2 bonds, which equals 1 centimeter. And 1, the way you pronounce this is tecolote length. What's significant is that the number 1 will go for your s orbital, 3 for the p orbital, 5 for the d orbital. I wish there was a 7 up here for the f orbital, but there isn't. So this is our standard length. Now our standard mass is going to take a little bit longer to explain. So if you saw the Bill Nye video, 1 kilogram or 1 liter of water is equal to 1 kilogram. And 1 kilogram is 1,000 grams. So I put 1,000 grams of water. The molecular weight is equal to 1 mole. The molar ratio, 1 mole of H2O to 2 moles of hydrogen. 1 mole of hydrogen contains Avogadro's number. So I got the number of particles that way. And here's the answer, 6.68 times 10 to the 25th hydrogen particles. So now, since we did hydrogen, we have to do the oxygen. So it's the same process, except your molar ratio is different. It's a 1. Up here is a 2. So for oxygen, we get 3.34 times 10 to the 25th oxygen particles. Now this is a part where I got the kilograms. So from hydrogen, from up here, this amount of hydrogen, well, 1 particle of hydrogen contains 1.67 times 10 to the 27 kilograms, minus 27 kilograms. In total, it will give you a 0.11 kilograms of hydrogen. And this is just to make sure that at the end it equals 1 kilogram. Otherwise, it's all wrong. So I got the oxygen, the 3.34 times 10 to the 25th oxygen particles. So 1 oxygen particle has 8 protons and 8 neutrons. So what I did is I took the weight of all of them. Here's the proton, neutron, and the average weight. The proton weight, the neutron weight, and the average weight. So from the proton's weight of the oxygen, of the total protons, if you count neutrons as protons as the weight, you get 0.894 kilograms So the protons from the hydrogen in the water plus the protons of the oxygen is equal to 1.006 kilograms. So if you count all the protons and neutrons in the oxygen, and you do this equation using this, you get 0.8958 kilograms. So the protons plus the neutrons of the oxygen, protons from the hydrogen, neutrons from the oxygen atom itself is equal to this amount of kilograms. But then, since it's made out of 2, I took the average also. So I actually did the amount of protons and neutrons together of oxygen will give me this amount of kilograms. The protons plus the average, so this plus the average is equal to 1.007 kilograms. So the most common number is 3, so my end result better have 3 sig figs. So I took the 3.34 oxygen particles. So one oxygen has 16 protons. If you count the weight of the neutron and the protons as the same, up to 3 sig figs, it'll give you 5.34847 times 10 to the 26 protons. So that's the amount of protons total of the oxygen, not including the hydrogen of the water. So together of the hydrogen particles, which is way up here, right here, plus the amount of oxygen protons, which we got from right here, is equal to 6.017 times 10 to the 26 hydrogens or protons, however you want to call it. So we got the 6.017 times 10 to the 26 hydrogens. Since we're rounding off to 3 sig figs, so it's 0.02 times 10 to the 26 hydrogens is equal to 1 kilogram, or 1 T mass, or tecolote mass. And so this is our standard measurements. For time, we're still going to keep the same time from the book. I actually like it. That's why I didn't want to change it, but I could change it based off of hydrogen, but really I just want to keep it. That way at least something's still the same from the whole book. I mean, I will show you guys my physics exams, but really I hope high school students or students learning chemistry will start from Bill Nye and then see my videos, and hopefully you do your exams based off of mine. So when your professor or teacher asks you, where did you learn how to do it this way, hopefully you can redirect them towards these series of videos, and hopefully I could actually win a Nobel Peace Prize. The reason I'm doing this is because I'm out of money to continue my education. So instead, I'm actually just reading and doing everything